Today we're going to be doing the solubility lab. Now, in this lab, what you're going to do is you're going to dissolve a solid potassium nitrate into water, and then you are going to record the temperature which it starts to crystallize out of solution, which is called the saturation point. Now, I'll go over the procedures in the actual lab. Let's start with the pre-lab questions. So it's going to be important to know what a solute, solvent, solution, and precipitate is. Those are some basic vocab words for this topic in chemistry. So what you're going to want to do is on a separate sheet of paper, write down these, answer these questions on a separate sheet of paper, and there'll be more questions on the back, but let's get to the work so I can take you through one sample calculation. So the first thing you're going to need to calculate is the GFM of KNO3. I'm giving you the answer, it's 101, but I want to see the calculation done at least one time. You don't have to do it 6 different times, but just once is enough, but it does need to be done once. So now for the first trial, what we're doing is we're dissolving 10 grams of water, 10 grams of potassium nitrate into 10 milliliters of water. Now, each trial changes the amount of potassium nitrate, and then the water is going to stay the same. So the first thing we want to do is figure out how many moles that is. So the GFM is 101, the grams of solvent or solute is 4, we want moles. We get 0.039 moles of potassium nitrate. Okay, now the next thing we would do, this part you have to get from the lab. That's why it says in lab right here. Basically, when you dissolve the 4 grams of potassium nitrate into 10 milliliters of water, it's not going to make 14 milliliters of solution. It doesn't work like that. Turns out it might actually, but in this case it doesn't, because it actually has to do with stuff that's a little bit more complicated than we need. But basically the potassium nitrate kind of fits in between the water molecules. So because it fits in between different water molecules, it actually doesn't take up as much space as it normally would. So it actually increases the density of the water, which is why it's not a direct addition of just 4 and 10 make 11. Even when you mix 2 liquids together in water, sometimes they don't directly add. Like if it was 4 milliliters of alcohol and 10 milliliters of water, it's not going to equal 14 milliliters of a new solution, believe it or not. Not all the time. Sometimes it does, sometimes it doesn't. So you just have to be careful about that. So these have to be taken once the 4 grams is fully dissolved into the 10 milliliters of water. So you're going to do these numbers once you're done. You'll take the thermometer out and then just look at the volume of the water. The next thing would be to convert that to liters. That should be easy. 0.011 liters. And then the next part is the molarity. And we get 0.36 molar KNO3, or 3.6 molar. All right, and then the last thing that has to be done from the lab is, so remember, this part has to be taken directly from the lab once the solution is fully dissolved and with the thermometer not in the solution, because the thermometer will add extra volume, obviously. There'll be pictures of that attached so you can get this reading without the thermometer in. And then you're also going to have to get the temperature at which the material started to come out or precipitate out of solution, which there will be a picture of that attached. So you're going to need this temperature. You're just going to get those from the photos as well. So you're going to get this and this from the photos that are attached to the lab, and then that is the information that we need to do the second half of the lab. The rest of it actually doesn't really matter. That's just calculations to see if you know how to calculate moles, and I want you to calculate molarity, and it's practice, so that's great. But ultimately, it doesn't really matter for the next part. For the next part, what we're going to do is we are going to graph this and compare it to table G. So when we graph this, to set up the graph, it's pretty simple. The y is going to go by single grams up to 14, 0 through 14, and the x is going to go 5 per box, or I did every other box is 10, which is 5 per box, up to 100 C. And then you are going to graph the amount of grams and the temperature that it precipitated out. And what I want you to do is, in addition to that, you are going to graph the graph from table G, which is for KNO3, and you are going to graph it on this curve as well. The trick is, table G is in 100 grams of water. This is in 10 grams of water. So what that means is you're just going to have to take the table G numbers at 2, 4, 6, 8, 10, 12, and 14, which is the numbers that we graphed here, right? So instead of, sorry, not 2, but instead of 4, 6, 8, 10, 12, and 14, since this is in 10 grams of water, to scale it to table G, we're going to do 40, 60, 80, 100, 120, 140 grams. So what I'm going to do is, in a separate video, I'm going to show you how to graph the table G graph and this graph onto one. They should look the same because that's essentially what we did, but we'll see how they work out when we do that in the second video. The last thing I'm going to mention is the questions at the end. So on a separate sheet of paper, this is going to be right after the pre-lab questions. You're going to answer all these questions. Why did you need to heat the solution in the test tube to make all the KNO3 dissolve? If you know the rules for solubility and how temperature affects solubility, that should be an easy question to answer. What else could be done excluding temperature to make all the KNO3 dissolves? So there is some other things. It has to do with, again, solubility rules, so you can talk about that. Remember, we want all the KNO3 to dissolve, not to make it dissolve faster. That doesn't really matter. We want to make more KNO3 dissolve. Would pressure affect solubility? Again, this is out of the notes. Does stirring the solution change the amount? It's in the notes. What are some other methods that could speed up the dissolving process? That is definitely in the notes. Does increasing how fast something dissolves affect the amount of material that can dissolve? Again, in the notes. Factors that do affect solubility, these are all easy. What is happening to the molarity of KNO3 while it is precipitating out of solution? That one's tricky, okay? So in this question, it says when the solution started to lose KNO3 from the water, it started to literally fall out of the solution, what was happening to the amount of KNO3 dissolved in the water? If you know that, then think about the molarity formula and then say, well, what's going to happen to the molarity as this happens? Meaning, as the water gets colder, you're losing KNO3. Well, if you get the water cold enough, you'll lose all the KNO3. So then that should explain what's happening to the molarity. You should be able to figure out what's happening to the molarity there. That one is we could put a star on it. That's actually requires a little bit more involved thinking. 9 is easy. If you can answer 8, 9 should be no problem. You actually should probably skip 8, answer 9 first. And 10, what is one possible use for recrystallization, for the recrystallization process that was used in this lab? This one I'm going to talk about because we don't really mention this. The real benefit of recrystallization is when it's done slow. So we're doing like fast recrystallizations because we just want to figure out when the material hits its saturation point. But if you do it really, really slow, it turns out it is a purification technique. You'll actually take impurities and leave them in the water and get a purer product, in this case, the potassium nitrate, out. You'll get bigger, cleaner crystals that have less impurities in them. So that's what it's ultimately really used for. That's one of the main techniques for recrystallization. And I should have an attached video on this that actually shows you a slow motion recrystallization. Hopefully I can find a video. If not, I'll have to use my phone and time lapse my own. Either way, you're going to get to see it. And then again, there will be one more video where I go over the graph in a little bit more detail. I'm going to actually set the graph up or start it with you.